everyone, and thank you for joining us today as we explore the world of induced seismicity. My name is Al Kassam, and I'm the technical coordinator at CSUR. On behalf of Dan Allen, our president and CEO, and Stephanie Smith, our events and operations coordinator, I welcome you all to the continuation of our technical webinar series. At this time, I want to take the opportunity to thank our corporate sponsor, Calfrac Well Services, for their continued support. I also want to thank Stephanie, as always, who is in the background and controlling the show, for putting all the technical aspects together so we can bring this to you today. So today's webinar is slightly different in that it is in collaboration with Geoscience BC. Our guest from Geoscience BC will expand on the program a little bit more. But really the objective of today's session is to highlight young geoscience researchers and their work in the area of induced seismicity. The session today will be moderated by Dr. Brad Hayes, who will also introduce the speakers. But before we get to that, I have a couple of quick announcements to make before we get started. We do have a full agenda today, so I'll try and make it very, very quick. Our next webinar is on Wednesday, September 30th. We have Kathleen Dory, a managing partner at Petrel Robertson Consulting. She will expand on the intricacies of seismic analysis for unconventional reservoirs. So again, this is Wednesday, September 30th. Registration is open. Our next session with Geoscience BC will happen on October 20th. The topic will surround groundwater and geothermal concepts. We have two speakers, Maximilian Getz and I forget his last name. Sorry, folks. And Theron Finley. Again, registration for this is open October 20th. Please note the time. It's at 11 a.m. Calgary time. And finally, we also have set up and open for registration this October 27th webinar, Liquids in the Lower Montney, Investigations Using Fluid Dynamics Data. Alison Gibbs from Canadian Discovery will delve into that topic. We're also working on a series of other events that are coming up before the end of the year. Now, given Monday's announcement with the BC election, we had BC Government Day #1 set up for October 16th. That has now been changed to November 25th. So please note that. As we get more information, we will release it and open it up for registration. As you can see, we're working on a lot of things. So if you do have ideas and comments and suggestions, please contact us. We'd love to hear from you. While this disclaimer slide is on the screen, I will quickly go through the logistics for today. I'll hand the show over to our partners at Geoscience BC shortly. For those not familiar with Zoom, as you hover near the bottom of your screen, a menu option or menu bar will appear. Please use the chat button to communicate with Stephanie or myself during the presentations. And please post questions and comments for the speakers in the Q&A option. And Brad will relay your questions and comments to the speakers. Okay. So please welcome Carlos Salas, Executive Vice President and Chief Scientific Officer for Geoscience BC. Take it away, Carlos.
Thanks, Al. Good morning, and thanks everyone for joining us for the first session of the CSUR Geoscience BC series, Celebrate Young Geoscience Researchers, highlighting induced seismicity. I'm Carlos Salas. I'm the Chief Scientific Officer here at the Geoscience BC. And for those that don't know who we are, Geoscience BC enables responsible resource development and encourages investment through independent, relevant public earth science about British Columbia's minerals, energy, and water resources. We work collaboratively with resource sectors, academic communities, Indigenous groups, and governments resulting in nonpartisan, unbiased, and credible Earth science. Since 2005, we've completed over 80 energy and water research projects, and these results are freely available, and the reports are peer-reviewed. And today we're going to be highlighting our scholarship program. We feel it's a great way to encourage and support the next generation of geoscience researchers. Through a volunteer scholarship award committee made up of academics, government, and resource sectors subject matter experts, we award up to 10 scholarships every year. And so far, we've invested over $600,000 into the program since 2007. And I'd certainly like to thank CSUR for creating this opportunity to hear from two of our 2020 scholars this morning. I'm looking forward to learning more about their research and also about their opinions in the future of Canada's energy industry. But before I hand it over, I'd like to introduce Randy Hughes, who recently joined us as the Manager of Energy and Water. And Randy, before we move on, could you say a few words?
Thank you, Carlos, and good morning, everyone. In my new role as the Manager of Energy and Water at Geoscience BC, I'm looking forward to working with all stakeholder groups, including the oil and gas industry, to continue to identify and help solve the geoscience challenges faced by everyone in the responsible development of resources. I have a great deal of science experience in the oil and gas industry in Western Canada. I've had the pleasure of working for some of the best in the industry, including Dick Cascane, Clay Riddell, and Jim Reimer. And for the past 7 years, I've worked on the technical challenges of developing the Montney play in Northeast BC. I encourage everyone to visit the Geoscience BC website to see the variety of technical projects that we're working on. And importantly, if you have an idea or area where research is needed, please reach out to me via the Geoscience BC website. Thank you, everyone. And with that, I'll hand it over to our moderator, Brad Hayes.
Brad, you moved.
Oh. Okay. Good morning, everyone. My name is Brad Hayes. Thanks, Randy, for the introduction. I'm the Outreach Director with CSUR, and I've been an enthusiastic participant in Geoscience BC's programs since about 2005 on the Technical Advisory Committee and as the author of several of the studies that we heard about today. My job here is to introduce our speakers, which I'll get right to, and I got a couple of questions for each of them that we'd like to sort of tease out some of their thoughts on their perspectives as students in geoscience today, in addition to the great research they're doing. So our first speaker today will be Paulina Wozniakowska. She's a PhD candidate in geophysics at the University of Calgary. She's working with Dr. David Eaton. She received her MSc in 2016 and her BSc in 2015 in Applied Geophysics at the AGH University of Science and Technology in Krakow, Poland. Paulina's current research focuses on geospatial analysis of induced seismicity. Before she returned to academia, she worked in the Czech Republic as a microseismic data analyst. She is current president of the UFC Student Exploration Geophysics Association and is a 2019 and 2020 Geoscience BC scholarship recipient. So over to you, Paulina, to talk about your PhD research, please.
Thank you, Brad, for the introduction. Hello, everyone. First, I just want to maybe clarify, I'm no longer a president of SEGA, although I will still work with our student research group. I will transfer more towards the CSUG representative, but I will still be around this group. Today, I want to talk about my research, and also, first, I would like to thank CSUR and Geoscience BC for inviting me and giving me this opportunity. Within my PhD, I'm looking into the seismogenic activation potential in Montney, and I'm using supervised machine learning for this purpose. And first, I will introduce the motivation of this study. Next, I will present the current state of knowledge regarding the factors that are controlling induced seismicity from hydraulic fracturing. Then I will give an overview on the machine learning used in this study. Further, I will describe how I developed the model and show the results, and finally finish with the conclusions. The area of the study is the Montney Formation, which is located in Western Canada in British Columbia and Alberta provinces, which is shown on the map on the left. It's one of the biggest unconventional places in Northern America, with significant amounts of natural gas liquids, and oil. It covers the area of over 130,000 square kilometers. It's mainly composed of fine-grained siltstone, and it's divided into upper, middle, lower Montney units. Some of the divisions also distinguish the additional division into middle and lower middle Montney, upper and lower middle Montney. The cross-section on the right presents the stratigraphy in the area. Montney overlays unconformably on the Beloy Formation. And I wanted also to indicate two more formations, which is the Bolt, which is part of the Rundle group, and the upper part, and the Precambrian basement. It will be, it was used also in this study, and I will briefly talk about it later. The main motivation of the study was to analyze the discrepancy in the hydraulic fracturing induced seismicity between British Columbia and Alberta provinces. Another point was to try to find a correlation between the injection depth, as the operation performed in lower Montney appeared to be much more seismogenic. The map on the right presents the seismicity divided by the origin, with orange star indicating the location of the biggest hydraulic fracturing induced earthquake in Montney, which occurred on November 28, 2018, and had a moment magnitude of 4.6. On the map, Montney seismicity is indicated by the red stars, and we can see that only it's observed in Alberta. There is no induced seismicity from Montney in BC. There is no induced seismicity in Alberta province from Montney. Yellow stars correspond to the induced seismicity from other places. For example, we have Duvernay Play and Horn River Basin. Quarries are shown with black stars, and green stars correspond to the tectonic events. Seismic monitoring areas in BC are shown in the inset, and they are outlined in with blue lines. We decided to analyze the seismogenic activation potential to better understand this spatial-temporal distribution of induced seismicity, and also try to find out why only specific hydraulic fracture wells are related to higher magnitude events. We implemented the machine learning technique originally proposed by Paulina et al. In 2018. Our goal was to investigate the geologic factors that are controlling the induced seismicity. And this approach is suitable for multidimensional datasets, which is perfect for this kind of geoscientific studies when we try to find more complex relationships. In this table, I just put together some of the recent observations from literature about factors that are influencing seismicity. For example, Amy Fox gave also a nice presentation at the Geo Convention about their study in Kisma area, in which they also take a look into the operational parameters that are influencing the seismicity. In general, we have two types of factors, geological and operational. So of course, geological factors cannot be controlled, and although they tend to dominate the seismogenic potential area, in the area, it's very important to understand also how the hydraulic fracturing operation impacts induced seismicity in order to develop the better seismic risk mitigation strategies. So the basic principles regarding the fault activation is well understood. So we know that induced earthquakes occur on pre-existing critically stressed faults, which are optimally oriented for the slip. One of the most important factors is also the vertical distance to Precambrian basement, as the deeper operations are more likely to activate the basement-rooted faults. Reservoir overpressure and tectonic regimes also influence, and tectonic strain. Tectonic strain in Western Canada increases towards the Cordilleran thrust and fault belt. So we can use the distance between the Cordilleran and wells to as a proxy to estimate the impact of the strain rate. Proximity to the bolt or below formation, also which was under the Montney, is also important, as there are faults in these formations that can extend up to the Montney formation. Apart from geological factors, induced seismicity is influenced by the hydraulic fracturing operation itself, especially by the injection volumes and injection rates, type of fracturing fluid, depth of the operation. And it was also observed that multi-well paths are much more often associated with induced seismicity, and it's due to higher cumulative injection volumes. Once we talked about the geological basics, I want to talk about some machine learning basics, and I will briefly introduce the approach I used. Machine learning is a part of artificial intelligence, including the algorithms that learn from the data. So the idea here is to use the known data to build the models and then make predictions using these models for unseen datasets, unseen examples. Deep learning is even smaller subset of machine learning, which relates to the idea of deep neural networks, but it's just not applicable for this particular problem because our dataset is just too small to implement that. Within machine learning, we can differentiate unsupervised learning when our data is not labeled, and this type of machine learning is used for different types of clustering or dimensionality reduction. In supervised learning, we build model using labeled data, and it's used for the classification and regression problems, so prediction of the class or some continuous values. These are the example algorithms that can be used, but I focus on the logistic regression at this stage. And I decided to use logistic regression for a number of reasons. So first, unlike the deep neural networks, logistic regression allows us to inspect the importance of each particular parameter in the model. So in other words, it allows us to assess how important each of the parameters was during the making of the predictions of the class. And second, logistic regression also gives us a chance to predict, opportunity to predict both labels and probabilities of the classes, which is particularly useful for this study. Logistic regression is derived from the linear regression, which is used to predict values without a limit, so from -infinity and to infinity. And as we can see on the left side here, if we use linear regression, it would predict the probabilities outside of the range from 0 to 1, which is obviously not correct. So this problem can be solved by implementing logistic function for the classification, because logistic regression uses the formula basically from the linear regression, but inside the logistic function, which allows us to squeeze the outputs into the desired range from 0 to 1. Looking closer to the formula of the logistic regression, we see that it consists of the logistic function, and also the input. Inside the logistic function, we have input parameters, which are our geological features, and the weights of the model. Bias is constant, it's just developed during the model calculation. So in what the model does during training, it assigns the weights, try to find the weights that for all parameters in order that generate the smallest error. And there are many different possibilities and different algorithms to calculate this error. In general, what I wanted just to mention is that the higher weights of the parameter indicates the higher influence on the classification result. And that's how it's calculated. And here are the steps that I used for the analysis. So first it was data collection and pre-processing, and it included interpolation of the data or some incorrect data filtering and preparing of the labels, because here I was using the binary classification, analyzing the wells that were assigned as seismogenic or non-seismogenic. And next step was the development of the algorithm. Then I calculated the feature importance. And finally, I extracted the predictions for the seismogenic activation potential for each of the wells. We investigated the geological factors that are expected to influence the induced seismicity based on some of the hypotheses that I mentioned in the beginning. Example inputs are visualized here on the map on the right. A pressure gradient was included as the overpressure in Montney is related to the occurrence of higher magnitude events. Then we used seismic SH max azimuth variance from the regional trend, as the presence of the pre-existing critically stressed faults may be manifested by the local rotation of the maximum horizontal stress direction. In terms of tectonics, we analyzed the proximity to the frost Cordilleran thrust and fault belt, and distance to the known faults. And distance to the thrust fault belt is included due to two reasons. First, we have high concentration of pre-existing critically stressed faults that can be reactivated. And also we can use it as a proxy to investigate the impact of the tectonic strain rate. We included the vertical distance to the bolts, as we assume it can be treated as a geomechanical basement consisting of harder carbonate rocks that can be connected with, for example, with Montney, and provide links by these faults. And also Precambrian basement was confirmed by other studies. And TBD was included to check the relationship of injection depth and induced seismicity. And depth index was introduced to investigate the relation of induced seismicity with respective Montney units. As I mentioned, lower Montney completions are suspected to be more seismogenic, and it's possibly due to smaller vertical distance to the faults. And the labels for our model were prepared based on the seismic activity observed around the hydraulic fracturing well, according to the following conditions. So we labeled well as seismogenic if all these conditions were satisfied. So if there was an event above magnitude 2.5 that occurred up to 5 kilometers from the well, less than 3 months after the start of the injection. And here are the main pre-processing steps. And the big challenge was in this study, the problem of the unbalanced data set. So the vast majority of the wells was assigned as non-seismogenic because it doesn't relate to induced seismicity. And it can lead to the biased probability estimates, and it requires the additional parameters in the model. For example, implementing class weights or using a random data shuffling to avoid overfitting. And the data was extremely sparse, so for some factors we had to use interpolation first to achieve the better coverage. Then the algorithm, the problem is that the algorithm treats all of our input data as correct and complete. So we really have to be careful about compiling as complete data set as possible. And I think that can be the biggest challenge, especially for if we are considering the faults, because sometimes our data set is not complete, or we don't have exact information about the existing stress in the stress state in the faults. Finally, some of the well input data itself was not correct. So sometimes I had incorrect TBD values, and I just I used the depth index to choose only the correct wells, and this resulted in around 6,500 wells that were used in the further analysis. So I mentioned about the depth index. So that was one of the input parameters that we used to investigate the seismogenic potential within the respective Montney units. And it was calculated by dividing the difference between the depth of the well and top of the Montney, and divided by the thickness by the Montney formation. And it allowed us to roughly estimate the Montney unit in which the hydraulic fracturing was performed, assuming that we divided into 3 equal layers. So I just wanted to indicate here that it's really a rough estimation, and probably in my next studies, I would like to expand a little bit more about on that. Table presents the ratio of the wells that were assigned to each of the Montney units. And we can see that here the ratio of the seismogenic wells is indeed the highest for the lower Montney, although this difference is not so significant. And here are the results of the feature importance analysis. So just remind, higher weights of the parameter indicate a higher influence on the model. So distance to the Cordilleran edge and injection depth were indicated as most important when considering the induced seismicity. Then we have this vertical distance to Precambrian basement, pressure gradient, and stage max azimuth variance. On the other hand, depth index, the distance to known faults, and distance to the default have the lowest importance. So I would say the biggest surprise here is the low importance of the distance to the faults. And it may indicate that our fault database is not complete, and or specific fault types and their orientations should be analyzed in more details. I included here also ROC curve, which is receiver operation characteristics, and it's used to evaluate the model performance. So just the red dotted line indicates the accuracy of the random guesses. So here we can see that algorithm did very good job in assigning the class of the respective wells. And based on those probabilities that I extracted for each of the well that were interpolated and then normalized, we prepared the map on the right. And we can see that seismogenic activation potential concentrates within the monitoring areas, indicated by the black lines, and increases toward the northwestern part of the Montney formation. In this map, green dots correspond to the injection induced seismicity band, where majority of seismicity is observed. And this band was suggested by Cao et al. In 2018. So we wanted just to compare how it matches with our observations. So we can see that higher seismogenic activation potential in Montney corresponds to injection-induced earthquakes band only within BC, which can indicate that apart from tectonic strain in this part, some other geological factors or their absence can effectively inhibit the occurrence of the seismicity in Alberta. I want just to finish with some conclusions. The machine learning model helped here to identify the main geological characteristics influencing the seismogenic activation potential in Montney, such as tectonic strain rate, injection depth, and the distance per Precambrian basement. Activation potential is in agreement with current observations of the enigmatic distribution of induced seismicity between British Columbia and Alberta during hydraulic fracturing operations. Implementing more detailed and, for example, and other input parameters such as operational parameters are needed to improve analysis a little bit more. And here I wanted just to again repeat the influence of the complete data set of the fault and information about the stress state. And finally, analyzing the upper, middle, and lower Montney units separately in more details might help to understand the induced seismicity distribution and those trends in the depth. And here I would like to thank Geoscience BC and Microseismic Industry Consortium for the financial support of this study. I will be happy to answer any questions. I'm looking forward to our discussion at the end. Thank you.
Great, thank you very much, Paulina. That was an excellent presentation. I don't see any outstanding questions right at the moment. I've actually got one myself, but I think what we'll do, because of our full agenda here, is to move directly to Ali's presentation. And then, as you say, at the end, we've got a couple of things to discuss that we'd like to hear responses from both of you. So I will go ahead and introduce Ali. So Ali Mehrabifard is a PhD student in geological engineering at the University of British Columbia, where he's been since 2018, and he's working under the supervision of Dr. Eric Eberhardt and Dr. Doug Stead. Ali earned his BSc in Petroleum Engineering from Tehran Polytechnic in 2015 in Iran, and his MSc in Energy Systems Engineering at Seoul National University, South Korea in 2018. So he's certainly a well-traveled fellow. His previous experiences are in geothermal field hydraulic stimulation and fully coupled numerical and laboratory simulation of this operation. Ali is an active member of the SPE and Geothermal UBC student chapters. His main current research topic is on injection-induced seismicity in underground energy development. So over to you, Ali.
Thank you, Brad, for the introduction. So my voice is clear, right? Just gonna make sure.
Yeah, we can hear
Awesome. Great. So first of all, a special thank to Geoscience BC and CSUR for this amazing opportunity. I really appreciate it. And the point about my title, I changed it a little bit because I thought there's little that we know about injection-induced seismicity. So sorry about that. I had to change the topic. And as of now, is injection-induced seismicity, the importance of understanding fault-state mechanisms. And allow me to quickly introduce the co-authors of this presentation. Actually, I'm in the postdoc in our research group who is mainly working with machine learning on induced seismicity, and Mehrabifard, as Brad said, he's my PhD supervisor, and Branko Damjanac, he's a principal engineer at Itasco, another sponsors of ours, and he's also on my supervisory committee. And last but not least, here are the sponsors and collaborators for my work and that of our research group at UBC so far. I think the need to decarbonize the energy system is completely obvious, and the scientific and observational evidence are overwhelming. So I'm not really going to go through this slide, but I guess the main takeaway point from this figure is that if we look at the figure on the right, it is showing the gas production in the US and the CO2 emissions. And we can see shift towards production use of natural gas has shown promising results in reducing the CO2 emissions. So I would like to call it the immediate solution to tackle the global warming is natural gas. Okay. But shale gas development does include its own challenges and impacts, one of which is induced seismicity. And I believe we all know about induced seismicity and its mechanisms. But if we want to discuss more on the recent deep-induced seismicity, which has been observed in Oklahoma, we can get back to this figure and discuss at the end of the talk. In this slide, you can see some of the large recent induced seismicity events at BC. And although the linkages between fluid injection and induced seismicity are reasonably well established as a possibility, there are still many uncertainties and unanswered research questions. I'm not really going to go and read through all of these questions, but many of them point to the questions of susceptibility and how likely it is for a given well to be at risk relative to specifics regarding its geology, its completions, and its interactions with neighboring wells. To us, however, one of the most puzzling question is that why does induced seismicity happen in only 1% of the treated wells? Okay, now, if we consider all the stake and rights holders in shale gas development, then there is a common interest in answering these and other related questions. To do so, a key component is data. Data helps to identify cause and effect relationships and contribute to understanding what is happening down there and identifying solutions to avoid or lessen it at least. From research perspective, the tools we use in our work at UBC are very much directed at understanding the underlying mechanisms, which I will talk more about it in a minute, but we are data limited and therefore benefit greatly from collaboration with industry, where industry comes forward and shares their own data. And similarly, we believe the collective industry likewise benefits through increased public confidence. And if you're talking in terms of hazard mitigation, response systems like the traffic light system used in BC, in Alberta, and elsewhere, like in Oklahoma, provides a measure of managing uncertainty regarding susceptibility and avoiding a large event magnitude. But this is a reactive measure, and it doesn't guarantee a large event won't happen. Thanks to sparse population in BC, the risk of damage due to induced seismicity to the community is much lower than other regions such as Oklahoma. But there is still a risk, especially with respect to damage to surface infrastructure and subsurface assets of the operators themselves. For instance, if we have a very large event and we have a large slippage happens, then we could have shearing in the casing and the well becomes more and more costly. Okay, now let's get into some more details here. I will begin with discussing why it is important to look at the frequency magnitude distribution and not just the magnitude level itself. This has been a focus of research in our group over the past several years. There are a couple of examples in both shale gas in the UK and geothermal industry in Finland that by adjusting the input hydraulic energy, they could actually avoid large events. So the largest event in these two fields were about like magnitude 2.1, which could not really be felt at the surface. Okay, now let's talk about a little bit about this Potemkin-Richter relationship. The A value here is actually governs the rate at which earthquakes are occurring, and B value measures the proportion of relatively smaller events to larger ones. So as the B value decreases, so does the slope of this line. And therefore we expect to have larger events as it get like lower in the slope. And the other point I wanted to clarify here, in naturally induced seismicity, we think of A value as a constant, but in induced seismicity and where we are injecting fluid, A value is temporal. It's a function of how much fluid we're injecting. And there is another parameter which includes inside this A value. I'm just gonna skip for now in the interest of time. All right. Okay, now we know what the B value is. Let's compare the B value versus differential stress, which is the main cause to store elastic energy in a fault. And then when there is a slippage, elastic energy is released and we have like larger and larger events. On the left, you can see the comparison between B value and differential stress for natural seismicity. Schultz gathered these events from all around the world, and he estimates the differential stress based on the depths of the earthquake hypocenters. I have gathered published data set in the literature on induced seismicity in different regions involving different industries, including shale gas, hydraulic fracture enhanced geothermal systems, you can see here, and also wastewater disposal. Oh, just a quick note that more scientific effort has been focused on EGS industry, who are generally open in terms of sharing data. As you can see, I have like 11 EGS sites around the world in my data set, while only 14 data points in terms of hydraulic fracturing, noting that there are considerably more hydraulic fracturing operations than EGS operations. Okay, anyway, back to the presentation. If we consider the same differential stress estimation as Schultz did, I get the induced seismicity is about 10 times more sensitive to differential stress. And this is actually making sense because we are superimposing a trigger, which is injecting fluid on top of the natural state of the earthquake. And if we consider the actual estimation of the in situ stress, we can see it is about 40 times higher and more sensitive to differential stress. So as we said, as the B value decreases, as we are going down on the y-axis, we will have a higher chance to have a larger events. And let's look at the effect of pore pressure on B value in this site. And you can see it is also important. increased pore pressure result in a higher chance of large magnitude events. For the sake of comparison, I'm just gonna go through some operational factors here, including average injection rate and total injected volume. And as you can see, I could not really find a clear relationship between the p-value and average injection rate and total injection rate. And this is actually aligned with what we saw in our machine learning algorithm that I will talk about in a minute. I'm just going to skip that also. All right. So for the machine learning part, for empirical analysis, we compiled a data set of around 2,900 earthquakes and 17,000 hydrorefraction operations from 2014 to 2016. This is the work carried out mainly by my colleague Afshin Amini. The distribution of the wells and earthquakes are shown in the figure on the left. To this, we applied a spatial filter of 5 kilometers and a 3 months temporal filter in order to identify induced seismicity, so much like what Paulina has done for her work. Therefore, if an earthquake event was recorded as occurring within 5 kilometers of an active well and within 3 months from the start date of the hydraulic fracturing activity, it was considered to be an induced seismicity. And doing so, we got about 550 events in northeastern BC. All right. We also gathered some input parameters, which are called features in machine learning. And here are the input parameters that we use. They are, most of them are similar to what Paulina has described here, but I'm just gonna focus on a few of them. The pore pressure gradient and the local and regional azimuths from, of the maximum horizontal stress, distance to fault, and injection depth, injection volume, and well completion lengths, and also the abbreviations. The well completion length is basically how long is the horizontal section of the well bores. And in these figures, they're basically the same algorithm. Not the same algorithm as the Paulina used, but they're all coming from decision tree. Decision tree is just getting some features and has some trigger value. If the value is higher than some value, it's true, we go down a road, and then if it's not, we go down the other road, and we decide, the machine learning will decide about if a feature is important or not. So we fit in those features in our machine learning algorithm. We used decision tree, random forest, and gradient boost to see what is happening. And overall, yeah, and just to mention that on the x-axis, there are the abbreviation of the features, and on the y-axis, there are the coefficients. So if the weight is higher, it's more important in the stating that the wellbore is seismogenic or not. But they don't have really a physical meaning, just weight. Okay, so overall, we saw in these three algorithms that the geological parameters were seem to have a higher importance than operational parameters. Yet, it's the operational parameters that can be controlled to mitigate hazard. We have seen, interestingly, the completion length was seen to be an important operational parameter, in contrast to injection rate and maximum injection pressure showed to be less important. So you can see here the maximum injection pressure and the rate and maximum injection pressure, and also here. But on the other hand, we saw the pore pressure gradient and completion lengths are more important, and also the distance to the fault, as opposed to what Paulina has seen in her logistic regression models. I'm just going to skip this. If you have any question, I will get back to that. Okay, in this slide, I'm just going to show you the tools, because like one of the limitations of the machine learning itself is that they do not really tell you any explanation as why a certain feature might be important or not. Therefore, we think greater value and confidence can be gained by linking the machine learning outcomes to research into mechanisms by other tools. So here I'm just going to talk about the tools that we have at the UBC, the plan that we are actually pursuing right now. First of all, we have a servo-controlled triaxial machine, which is capable of simulating the stress, pore pressure, and temperature conditions deep underground. And we recently added a state-of-the-art ultrasonic velocity and acoustic imaging system, which enables us to continuously record the seismic data and periodically record the ultrasonic velocity tomography in the rock samples. We have like 18 sensors, which are both transmitter and receiver, and providing a very good 3D coverage over the sample. For those who don't know what the acoustic imaging are, they are analogous to induced seismicity, but at a much smaller lab scale. And we actually acquired the system right before the COVID lockdown, but after a few months, we are now back in the lab and have the system up and running, and are currently working on the calibration to get the kind of the magnitude and the source location of the events very accurately. In this work, we also consider the source mechanism, like for example, if that acoustic imaging was caused by attention or by extension or by shear and stuff like that. And then we have a very powerful numerical code developed by Wozniakowska, designed specifically to simulate hydraulic fracture. I will talk more about it in the next slide, but one of my goals is to verify the performance of this relatively new code against hydraulic fracturing test data we will generate in our lab so that we can apply it to field problems with more confidence. I have done some preliminary work on this verification using published data, as you can see here, and they are very well kind of matching. Okay, now back to XSite. XSite is a software that uses discrete element method to solve the partial differential equations in coupled hydromechanical environment to simulate complex and difficult multi-stage hydraulic fracturing. It is capable of to measure the stress shadow and stuff like that. It has shown very promising results in simulating the fracture propagation and interaction behavior in the presence of natural fractures and faults. And it is also capable to simulate induced seismic events. And it is one of my research objectives to verify the built-in algorithm that estimates the microseismic events by comparing results against actual lab tests. In this slide, I just wanted to show you the preliminary results of XSite verification against the published hydraulic fracturing experimental data. On the left, there is a acoustic emission results. Actually, acoustic emission results distributed in a sample, and it was recorded by acoustic sensors. And this experiment was done in sandstone, in a cubical sandstone. And there was a borehole in the middle, and the events are color coded. So if they are more red, they are more new, and if they are more blue, they are like from the past. The results are very promising, and you can see the acoustic imaging distribution are very similar. I can discuss the discrepancy a little at the end of the talk. Here's another example of using XSite, but at the field scale. Here I look at the effect of the stress regime on B value, and as seen in observations of natural and induced seismicity, the B value for the truss fault regime is the lowest, which means a higher chance of fault induced seismicity. It is well aligned with what I have showed you before in terms of B value and differential stress. The higher differential stress is equivalent to a truss stress regime. There is also another paper in our group by Amini, which focuses on comparing the Woodford in Oklahoma and Montney in British Columbia, which shows that the dominant truss stress regime seen in parts of the Montney results in an increased potential of large seismic events due to higher stored energy. Oh, and this is like the B-value comparison for normal strikes to truss. Okay. As I previously mentioned, we are currently designing a calibration technique so that we can accurately measure the magnitude of these picoseismic events or acoustic emission, so that we can analyze the frequency magnitude distribution analogous to actually induced seismicity. We want to find a more robust relationship between the differential effective stress and the frequency magnitude distribution parameters, such as seismogenic index and the value. Also, we wanted to look at the seismic sleep. And this is one of our interesting test set that we developed at UBC, where we have a pre-Sawcut fault with a low severity, and we can actually do a hydraulic fraction or hydro shearing on that and measure the seismic release energy and also the hydraulic energy. And just to sum up and wrap up, machine learning is just a classifying. It's just classifying the data for us. It is not really showing why a certain feature is important or not important, and it is a limitation on this side of the data analysis. But we think we can gain more value in analyzing the output of the machine learning with the state-of-the-art equipment tools. Thank you for your time.
Great, thank you very much, Ellie. It was great to hear your research. I certainly had to concentrate on that one. I think you're really pushing the understanding limits for those of us that don't have this kind of background, but I think this is exactly the kind of specialized research that both you and Paulina have shown that's really necessary to start addressing some of these key questions around induced seismicity. So we've got a couple of questions here that are open. Paulina, I believe, has answered a couple of the questions already, which is great. I'm just going to ask one or two of them that are outstanding here on the Q&A site, and then I want to get into a couple of the questions that we want to address in terms of your careers as researchers. So one question directed to Paulina that she don't think has addressed yet is from Doug Berenger, saying, was the volume per well, per frac stage, or per injection point? Some parameters should be looked at normalized to stage or to formation entries.
Yeah, so I think it can be the question to Ali. I haven't considered any operational parameters in my study, just geological features.
I'm sorry, yes, pardon me, Paulina, because Doug did ask a question, and you've already answered that in the Q&A session. I just recognized his name there, so if that's okay, then I'll go to these other couple of questions for Ali. From John, Ali, why do you think completion length is an important variable when injection rate and pressure are not? That seems counterintuitive to me. Perhaps completion length is correlated to total volume injected.
I think like this is something really interesting, and as I said, these are like pretty new, and we are still thinking about why it is, why our algorithm is showing such a result. But if I wanted to answer it like shortly, if we have a longer completion length, it means we are actually affecting a larger area, or if you wish, larger area of the formation with the pressure changes. And if we consider there are like randomly distributed fractures everywhere down there, there is a higher chance of having more induced seismicity and perhaps larger induced seismicity because we are increasing that area of disturbance.
Okay, thank you. One more question specifically for Ali from Wilson. Ali, the ultrasonic signals are very high frequency. Does this mean high frequency signals are meaningful in the field? How high shall we try to get to?
No, it's like basically in the rock samples when we are doing the tests in the lab, because everything is smaller, and we are going for higher frequency to get that analogous. Because in practice, if we want to measure the magnitude of the events in the lab, it's like the largest one would be about magnitude -5 or -4. But in the field, we're not really interested in those. We are just more interested in the higher one, I mean, in the larger events. And this is actually interesting. I'm just going to add this point. If we are considering the seismic slip, which is a hot topic right now, maybe in the field, we are not really able to hear those kind of high frequency because of the slow slip. And maybe we can also address this question in the lab in terms of seismic. So I hope I could answer that question.
Okay. A question from Pat McCullen to both presenters. If you were an operator, would you be using ML or deterministic slip on a fault modeling approach to assess the risk of an event occurring? So Paulina, do you have an opinion on this?
Yeah, I would say if I was an operator, I think I would prefer first to go for a fault modeling approach. As I observed when I was doing this study, the results that we are getting, it really depends on the input parameters that we are using. So you can just try to throw more parameters and sometimes it was just happening that featured importances were slightly changing. And I think it's related to the fact that sometimes our model is too simple. So for example, we didn't consider all the parameters. So it just works. So the model, it works with anything that we provide. So I would say in this case, the machine learning is not always the best approach, I think, because it really depends on how confident are you with your data. And with the modeling, I think it's something that you can, it gives you maybe more explanation on what is happening. So I would say first, I would start with the modeling, and then sometime, maybe based on the modeling, if we have some further observations, we can tweak our input parameters in order to decide what was really the driver or what is influencing in this case, because sometimes it can also provide some nice feedback on what's happening on the fault, for example, considering different parameters. So I would say start with modeling and then use those results to have maybe some more logic behind our machine learning model.
Ali, do you have something to add on that question?
I think, yeah, like I guess if it was me, I would go with both of them, and I would use machine learning, kind of like it's the powerful tool to go with the real-time analysis, and also, but if I want to get to the bottom of this issue of induced seismicity, I would definitely go with the modeling and using lab scale stuff.
Okay, we are getting near the end of our time. I think what I'll do, if that's okay, is I've got one more general question, I think, for both of you. There have been several questions addressed and answered in the Q&A box that I believe everyone can see, and I urge you to go and look at those answers, because I don't think we've got time to deal with them all today. But one final question for both presenters. Many operational and geological factors are linked. Is this considered by the algorithms, or are they assumed to be independent? Ali, why did you go first on this one?
That's a difficult question. So I would say, yeah, they are. It's super hard to kind of make them independent from one another. But at the end of the day, geological features are what we are given, right? And the operational features are those that we can control. I don't think the algorithm has anything to do with and it would just think about them as independent features, not really thinking about it, they are dependent.
Okay. Paulina, do you have something to add there?
Yes, I would say based on the presentation that I mentioned before from AV Fox, she mentioned that really it looked at geological factors were dominant. So it's still, there is influence of the production and injection, but like geology is the major. But in terms of like which are correlated, which are not, I would say it's good. One good approach is to maybe try to do the modeling with different set of parameters with different values, for example, of pressures, and then see how it correlates with the geology. But I think also there is some way to maybe try to do the correlation matrix just to see which features really are correlated with each other. But I would say, yeah, it's always good to have some other source of knowledge than just purely putting the features into the algorithm. Just try to dig more and just try to do more analysis on that before you put that into the algorithm.
Okay. Thank you. We do have a couple of questions I haven't gotten to yet specifically. Al and Stephanie, should I continue to go through these questions, or should we quickly go to the general questions, because I see that we're past the end of our time?
Up to you. If you want to continue, I'm okay.
Okay.
We're okay to keep going. This is
Okay.
pretty good dialogue, so yeah.
Yes, I agree, Al. It is. So let's keep going. Well, we've still got a good number of participants here. So a follow-up from Pat McClellan to Al Lee, and you addressed a question from Pat before. He's saying, just to caution, if you are using maximum surface pressure, you should not expect a lot of correlation, since it is most often dictated by the maximum wellhead pressure allowed. What matters is the bottom hole pressure, especially in the hydraulic fracture or the fault. And Pat's looking for your comments or thoughts on that statement.
Definitely, yeah. If you have the bottom hole pressure, that would be definitely better. But like what we have right now is just the wellhead pressure. So we thought we just put that in the machine learning. So as if you put more features in the machine learning, basically you have more robust algorithm and results. Yeah, for sure. If you have like those kind of bottom hole pressure, that would be way better. But now we just have the wellhead pressure.
Okay, thanks, Ali. I see one more outstanding question here that hasn't been answered yet from Peter. Paulina, I am puzzled by the difference of seismogenic activation potential between Alberta and BC. It looks like it is centered around the Fort St. John Graben, or Peace River Arch, and thrust belt. Can you explain this a little more?
Yeah, so first, our idea is just if we approach closer to the Cordilleran belt, we are getting enough tectonic strain to activate a fault. Like they're just more likely to be reactivated. But in terms of this concentration around Fort St. John Graben, this is a very good observations, because that's what actually we expect, that there are just significant faults that are connected with Montney. But it's just something that we just need to do more research on, just to make sure that that's the case. But honestly, like from my observations also, it looks that it's correlated to this Fort St. John Graben and the amounts of faulting that we have. And also it's proven by the lack of seismicity in Alberta, that maybe there are just not enough faults that are connected to Montney. They are maybe deeper, or it's just hard to say because the database was not really complete when I was doing this study. So I would say this is very good starting point, especially if you are taking a look on the Northern Montney and Kisma area, where we have lots of data. And I think that's the biggest, I would say, challenge with this approach. Like Ali was saying that, oh, for his study, the fault mattered. But for myself, for my study, when I was just analyzing the whole Montney formation from the regional scale, I think that's a kind of a trade-off. We can do some regional analysis, but there is a chance that we are lacking something if our data is not detailed enough.
Very good. Well, thank you. So I think that we've addressed the outstanding questions. And again, just to repeat, some of them have been answered online within the Q&A box, so we haven't read them all out. But I'd like to take the opportunity here just to switch gears a little bit with our two researchers. And both CSUR and Geoscience BC, I think, are very interested in understanding a little bit better, and I hope a lot of our audiences as well, in terms of the motivations and outlooks of people like Paulina and Ali in their current research, and because things are a lot different in the world today than when many of us went to school and started our careers. So just a general question for both of you. What led you to undertake your current PhD research? We know a bit of your background, but what got you going on it, and is it has it, I guess, turned out to be what you thought it would be? So Paulina, I see you on the screen, so why don't you start?
Mm-hmm. Yeah, so I started by processing microseismic data in the company, but it was more related to this basic routine stuff, which was like event picking, detection, location. But we had some projects from Canada, and I think what's better now. So first, what happened? I just decided to expand a little bit more my knowledge, and it was a little bit of luck, a little bit of coincidence that I finished in this group, actually, because it everything was, I didn't plan it for a long time. It was a matter of as I said, luck that I got a chance to join the group of Dave. But the main, I think, motivation to start the studies was just to try to understand better what is happening. Because if you're processing data, you sometimes you're not involved so much into that because you have your reports, you just do what you have to do. But especially in like smaller companies, it's more about just doing your job, but there is no so much time on the research and really focusing on understanding what's going on. So I think that's the biggest motivation. And right now I'm just more time I spend on my PhD, the more people I meet, I just see it's much more easier when you have big research groups that we can talk and just share experiences and learn.
Great, thank you. Ali, can you relate your thoughts on this question?
Yeah, like my best motivation for starting a PhD was that I really love doing research, and I really enjoy studying papers and doing some new work and kind of trying to tackle the problems which is happening actually in industry and stuff and academia. And the other main motivation is that I really want to have my own research group someday. That's the main reason why I'm doing a PhD, to become a faculty member and hopefully a consultant at some companies, or having my own company. I don't know. It's vague for now.
Great. Okay, well, thanks for that opinion. I've got one more question I'd just like to sort of get your thoughts on. And, you know, we that are working actively in the industry right now, the fortunate few of us anymore, we've got, you know, certain outlooks on where the industry is going, the oil and gas industry, and related, you know, related geoscience careers, whether they be in research, regulatory, or other areas that impact on the oil and gas industry. But from your perspective, being at major universities and deeply involved in research, what perspectives do you have on future geoscience careers? Now, Ali, I think you've already gotten into that a little bit from your own perspective, but do you see there being attractive opportunities in resource industries or related functions, including oil and gas? So, Ali, why don't we start you on this one?
To be honest, I'm really not that hopeful in the future in terms of like being still a petroleum engineer, because there is so much movement against them. But in terms of actually applying injection-induced seismicity, there are more opportunities like in geothermal, in mining, and stuff like that. So I kind of see myself more in terms of like going towards shale gas and geothermal, but I don't know if they are interested to get a PhD kind of person or like an undergrad to work with them. It's not really clear to me. For example, I'm seeing my undergrad students, they are going to work and they are actually earning a lot of good money right now, but I don't know what future holds for us as a PhD student, if there is a good market to work in it or not. I really don't see.
Okay, thank you for that. And Paulina, your perspectives?
I try to be optimistic on this one. And for now, I decided just to do my job, really learn as much as I can, just really investigate what's happening here in Alberta and whatever the research group are focusing on right now, and just to focus on Canada right now, on Canadian cases of induced seismicity. But I think as a young geoscientist, like, we have to be aware that we just need to be flexible and learn also other skills, because it's hard to predict what will happen. And also I believe, like, speaking about new skills, and of course I'm thinking about like programming and all this data science, like it's a buzzword, but I think it first opens you doors for new opportunities. And also I just noticed it can help with the research. Sometimes it makes things easier. It's not only about running machine learning algorithms, but it's just having some tools that can help with the research. So I would say it's important to be open and just learn various things, not just spend all your time on your research, really digging into the details all the time. Just try to do something else.
Great. Great. Thank you very much, Paulina. I really appreciate, on behalf of myself and CSUR, the time and effort that both of you have put into doing your presentations today and in answering both the technical and more general questions. I think you've done a great job, and thank you very much. I'm going to turn it back over to Al to wrap things up.
Thank you very much.
Okay, great. Thank you, everyone. Yeah, excellent show, everyone, and very good questions and dialogue, and also some very insightful comments from our young geoscientists and researchers. So thank you for your work, your time, and your presentation today, Paulina and Ali. Thank you, Brad, for moderating. Thank you also to our partners at Geoscience BC, Carlos, Randy, and I know Richard was online. So thank you, guys. Thanks you again to our sponsor, CalFrac Well Services. And last but not least, thank you to all of you for joining us, all those that hung around to hear my final comments. And once again, our next webinar is on Wednesday, September 30th with Kathleen Dory of Petrel Robertson. Her talk will surround seismic analysis for unconventional reservoirs. So see you then. Enjoy the rest of the day and stay safe, everyone. And goodbye. Thank you.
Bye.
Goodbye.
Thank you.
Bye-bye.